Welcome to TechTalks Stuttgart. I'm very excited that after, I don't even know how long we haven't met, but more than 2 years probably, we can be back together here at Gutbrot and celebrate 2 very interesting talks, both related to tools for camera. So the first talk will be the lens distortion tool from Marius Jerschke. He's from ZEISS. And the second talk is Programmable Optics for Computational Photography by Andreas Engelhardt, University of Tübingen. TechTalks is a format in which we invite young researchers and people that work in companies on tech tools and things that relate to media creation to come and speak to the audience of interested students and professionals from the greater region of Stuttgart. It is initiated by Animation Media Cluster Region Stuttgart, AMCRS, MFG Baden-Württemberg, Filmkommission, Region Stuttgart, Hochschule der Medien and Filmakademies Animationsinstitut. So without further ado, I would hand over to Marius for his talk on the lens distortion tool. We'll have Q&A after the first talk, and then the second talk will start. And at the end, we have also the opportunity for an open microphone to announce or spread the word for interesting things. So I'll switch over to Marius and see you again later.
Hopefully you see all my screen right now. This is just a short introduction why ZEISS decided to join visual effects, or why we want to do something for visual effects, because we see that there's a big change in the industry. We have more visual effects, we have virtual production, and in all of these fields you need a lens. And normally we do only a physical lens, but now for the future we will provide a digital lens as well. And our first step, providing a digital lens, or at least providing the lens characteristics of a lens, we start with our first tool, and we come to this tool later. But before we come to it, I explain what our thoughts behind it are. So when we take a look at the really simplified visual effects workflow, as you can see here, we have the pre-production, the production, the post-production. And the most important parts here for us now is matchmoving and compositing, because we thought we can provide the distortion and the shading as the first 2 lens characteristics, because they are very important to perform a correct matchmoving and correct or compelling and compositing for good visual effects. What we thought is that the lens characteristic of a lens has a major influence on visual effects, because the look of the lens will dictate how the visual effects artist will create the visual effects. So the bokeh, the chromatic aberration, the distortion, and the shading. And we start now with the distortion and exposure fall off, because for us it's very simple to provide these now. With our pipeline and our optical design department. And we also think that they are the most important 2 characteristics to perform matchmoving and compositing. So as you can see here down below, I hope these are 2 GIFs animate. I hope you see the GIF animating. So on the left, you see the distortion. So straight lines are slightly curved. For example, a building is not straight, it's slightly curved because of the curvature of the lens itself. And then the same goes for the exposure fall off. So in the center of the image, it's slightly brighter, and on the edges, it's slightly darker. And when we look at matchmoving, here you need to know the distortion information, because without the distortion information, maybe the match move is inaccurate or even not possible. Why? Because how does a match move work? Actually, you have your DOP. He's doing physical movement with the camera. Then you are using software on the computer to replicate this movement to get a virtual camera or a digital camera that you can use then as a visual effects artist to create CGI or to composite your final image. And in the process of the software, where the software gets the recorded footage and try to track the points in the image, it's important that you remove the distortion before you let the software track the points in the image. Because if you have distortion in the image, the points are maybe accelerated on the edges of the image or are slightly slower. So the software will think that the points have a different movement than when you, instead of, before, when you remove the distortion beforehand. So it's very important that you remove the distortion before you start match moving, because then you get a more accurate result. And from compositing, you need the shading or the exposure fall off and the distortion as well. Why? Because the CGI comes clean out of the computer. It doesn't have any lens characteristic at all. It doesn't have distortion or chromatic aberration or shading, nothing at all. And because of this, you need to remove it from the footage. Then you can combine it with the CGI, and after the combination of both, then you can re-add the distortion and the shading. Normally what they do is they just remove the distortion, combine everything, and then they tweak a little bit on the brightness values to match the CGI in the shading values. But in our case, we think it's even easier to remove it also as well beforehand. And with our tool, it's now possible. And how do they get the distortion right now, or also in the last decades? They did something called lens evaluation, or also called lens grid process. So what they do is they use the camera and the lens they also use for the production. They take a photo or a quick recording of the checkerboard or lens grid in a certain distance. Then they feed this recorded footage into a software. The software analyzes the curvature of the lens grid itself, and then generates a ST map. A ST map is just the image with certain color values in it, and compositing tools or match moving tools can read these color values to manipulate the image then, for example, to remove or add the distortion onto an image. And the problem with this is that the focus distance of a lens has a major influence on the distortion. So you can't just take one recording of a lens grid. You need to take a photo basically for every change on the lens you do. But this is not possible because you can't do something for infinity. You can't do any step because then you have infinity photos in the end. So they try to get as close as possible to frame accurate distortion, but they can't. So what they do, for example, Industrial Light and Magic, they do 12 for each lens. Other studios maybe just do 5 different photos. And then the visual effects artist in the end also needs to analyze every photo and make sure that that you get your information out of it. And as you hear out of it, this is a really time-consuming process, and you can make mistakes in the recording, you can make mistakes in the analyzing process, and sometimes the visual effects studio doesn't get any information because the production company forgot to make the lens grids. So this is a really time-consuming, error-prone, and analog process. And for example, for exposure fall-off, there is no process at all. Normally, they do it by eye and hand on the PC and match the values. And in certain cases, they do a process. It's called gray cards, where they just take a photo of a white card, and then on the recording, they see the vignetting, the exposure fall-off, and then they can replicate it in the compositing process. But yeah, for the distortion, they have this complicated process called lens evaluation. And we thought, let's skip this complete process, and we want to provide you a tool. We call it the ZEISS Syncroft Mapper that brings you frame-accurate distortion data and frame-accurate shading data for match moving and distortion. And Syncroft is our ecosystem and web platform where we will launch also future products, because we are currently also working on other products. One will be launched in October, maybe, if we can make the time frame. And then we are also working on other projects. So be prepared to see something cool coming there. But the mapper is really our first step. And now we can jump out of this presentation right into the tool itself. So can you see my screen still? I don't know, because the tool says something. I just reshare real quick. Okay, now it should work. So here's the mapper itself. It's really simple, intuitive. Everyone can use it. This is our UI version. So we have 3 simple steps. The first step is import the data. The second step is configure, check your metadata. The third step is generate the maps you need. And then we normally talk about the fourth step, the integration into a compositing or matchmoving software. So in 4 simple steps, you get your distortion and shading instead of this complete, 2 days preparation of lens grids. And this is really cool. And on top, it's frame accurate. And this is really cool, I think. And now let's take a look how it works. I will do the happy pass. So I will do it really quick first to show you how fast it works. And then afterwards, I show you it in more detail. So first, I just drag and drop the EXR sequence and the ZSV file. In combination, here you can check your metadata. You see everything went fine except one thing. We did this on purpose to show you this feature that you can also integrate everything that is missing, because maybe your file is corrupted or you don't have the information of the metadata, then you can also enter it manually. So this is really cool for everyone that just, makes pencil notes on set instead of doing a real metadata workflow. And then after the check of the metadata, you come to the checkout, to the generation process of the maps. You select the folder. I select one just on my desktop. I want ST maps and I want multiply maps. And currently it shows a price of €0 because our software is kind of smart. If you already done the shot, and you want to do it again because you lost the files or something, then the software will see, it won't charge you twice for the same shot. So I did the shot a lot to showcase. Because of this, it's €0. And now I hope it works. Sometimes it doesn't, because maybe I have not the newest version on my PC, but now it works perfectly. So it generates the maps now, and it takes a little bit of time because we not generate just one frame, we generate the frame accurate sequence. And when we look now in the folder where I saved it to, so we have a distort sequence now, shade sequence now, only 3 frames, but we come to this later, undistort and unshade. And then when we go to nuke, for example, this is a really simplified node tree of a compositing. Normally it's much more complex, but as you can see here, just for explanation purposes, here's our test footage. This is the footage I generated the maps for. And after the footage is imported, you can use the STMap node. You plug in our undistort STMap sequence, and you get a frame accurate distortion. When I disable and enable it, you can see that the image is corrected correctly. And the same goes for the multiply map, the unshade in this case. And when I look through here and deactivate it, you can see that the map works perfectly. And then you put in your CGI, and then afterwards you re-add your distortion all over it, and you see that the distortion also distorts the CGI. And the same goes for the multiply, the shading as well. So this was really the happy pass to show you how quick it now goes or can be to get your distortion and your shading and even frame accurate. So it's really easy and everyone can do it. Especially companies that don't have the time to do a lens grid, now they can get the distortion as well. So when we jump back into the tool, because some clients ask us, do we read any pixels? And now we don't read any pixel, we only need metadata. For this, for example, there's also the the possibility that you can do it manually if you only have pencil notes, and then you can select your camera, and then you can select your recording format, and then in the end you get your maps. And on the other hand, you can also just drag and drop CSV file, for example. CSV file is just the Excel sheet with all the metadata in it. So we don't need any pixel information at all. But we thought for a visual effects company, it's easier to use EXR files because normally they work with EXR files. And now we can take a look a little bit closer to these categories here, because I think this is really cool here. The first thing here, you can see really the changes in the focus distance per frame. And in the future, we will also support zoom lenses. And then you can see all the focal length changes here as well in the third graph. And this is really cool, I think. This is, I mean, no other tool can do something like this. And this is really cool. And then here you can select your camera. Currently, we support ARRI, RED, and Sony. Your recording format of your camera, your lens. Currently, we support ARRI ZEISS lenses, master macro, master primes, some of our ZEISS, but we want to support every ZEISS lens. So also dump lenses in the end, not only smart lenses, you know, with a little, with our extended data where you get your metadata. So this is basically it. This is how our tool works. It's very simple. And we also offer a command line version. So you can, if you have a professional environment where you don't need the UI version, where you can click everything, you just need the code to implement it into your pipeline. We provide this as well for Mac, Linux, Windows, for every operating system. So it's system independent, it's frame accurate, it's convenience, and yeah, that's it, basically. And now, if you have questions, feel free to ask me anything. I hope I can answer everything.
Okay, very impressive. Thanks, Marius, for this presentation. Are there any questions? Yes, please.
Maybe one question regarding the calibration process. Can you say something about how you actually generate those distortion information, and do you do that for every serial number or every? Is that like more of an average?
Yeah, this is a good question actually, because this is a question we hear a lot. We don't do it per serial number because we found out that the tolerance of our lenses is so small that our distortion model or our optical design data that we provide, because how we do it at ZEISS is that our optical design engineers that build the lens, before they build the lens, they simulate the lens on the computer. And this information now we can use to provide the distortion and the shading, and in the future, hopefully even more. And this optical design data is still more accurate for our lenses that comes out of the, you know, that has the small tolerance. Of course, if we're talking about, for example, a Panavision lens that is has maybe some, you know, I don't know, some cracks in it and is old and used over years, then our tool won't work. Our tool is meant for really for clean lenses that has, all the proper settings that the lens should have. And we have also implemented this small message here in our tool that says hardware modified or damaged lenses decrease map accuracy. But for example, if you have a color filter in front of your lens or a nylon to get a cool looking lens flare or something like this, this won't affect our tool because we don't need the image at all. We only need the metadata out of the lens. And because of this, it works. Potentially, we could do it serial number based, but we don't need to. Yeah.
That's good answer to the question. Thank you.
Yeah, exactly my questions also.
Exactly.
Yeah. Can you? Is there a way you can incorporate also the traditional way of doing lens grids? in the tool? Is there a possibility to come also from the side?
You mean that you can do the lens grid analysis in the tool itself?
Yeah, in the tool.
No, I mean, that's not our goal, because our goal in the end is really to replace the lens grid process, because we think it's not worth it anymore. It's so time consuming, and our goal is that we replace the lens grid itself. But of course, many visual effects supervisors told us, oh, I'm afraid, I fear that maybe I lose some information. I will still do my lens grid. Okay, you can still do your lens grids just to have it in the backup. But with our tool, it's just simply and more accurate in the end. Yeah.
Okay, so maybe question from my side on the workflow. Is this a installer-based application, or is it a cloud service where you send files into the cloud and process them?
Yeah, no, it's a standalone version, because before, for example, for extended data, this is our connection of the smart lenses where you can extract or record externally the metadata. For our extended data connection, we had this plugins for Nuke, for example, or After Effects, where you can then use it in Nuke. But we thought, no, we want to be system independent now, that everyone can use it. And this is a standalone version that you can install on Linux, Windows, Mac, and then you just import your metadata, and then you get your ST maps and multiply maps, and then you can use these maps in any tool you like. I mean, you can use it in Nuke, you can use it in 3D Equalizer, wherever you want. And this was our goal, that it's system independent and everyone can use it. Yes.
And maybe related to that, can you say something about the pricing structure for it? Because everything seems to be tightly integrated into, you mentioned that a shot that's been paid once can be reopened and reconfigured, right?
Yeah, I mean, you never get charged twice for one shot. So if you have generated the maps for one shot, then you never pay twice for the shot. But how we charge on our website, there is a category. I think this is easier when after our talk, you go on our website and check the list there. But how we do it basically is that we charge per shot. Our first approach was that we try to charge per frame, but then we thought it doesn't make sense. In the end, everyone wants to save money, and then they just generate one frame, and then they pay just 14 cents or so. And now we thought we have a good Mittelwert. I don't know the right word for in English there. That compensate the time of analyzing lens grids, and yeah, it's just a fair price in the end.
Okay. Yeah. All right. More questions? Well, then let's thank the speaker one more time and prepare for the next lecture.
Yeah, hello everyone. It's a pretty intimate group today, so I guess I'm just going to do this the way it's planned. It's not going to be that fancy or applicant to your daily work probably, but it's hopefully sparked some new perspective on what lenses actually do and what you can actually do regarding capturing light overall. So yeah, I'm Andreas Engelhardt actually. I'm a part of the computer graphics group at the University of Tübingen. And today I have the honor actually to be here and talk a bit about programmable optics for computational photography. And hopefully at the end of the talk you will be kind of able to answer the question like why we have this kind of strange looking monochromatic pattern there and why we have some want to capture some blurry images to make them sharp again at the end. But the idea here is to have some encoding in our optical path and then do some decoding to reconstruct some image representation that has a certain attributes. And depending on the application, this might be kind of useful in the foreseeable future or in the long-term future. Anyway, a couple of sentences about myself, maybe. I studied at the HDM, actually, in Stuttgart here, did my master's at the University of Tübingen. I worked as a VFX artist, as compositing TD, also as supervisor for some projects. So I have kind of a perspective also from the production side and the, especially the visual effects and post-production side. Currently, I'm a research assistant at the computer graphics group, as I said, and PhD candidate supervised by Professor Lensch. And yeah, parts of this work that I'm going to present is definitely also done by Jian Chen. Credits go to him also for the slides, or parts of the slides. And some other parts are basically based around my master thesis and some other works that have been done in the meantime by other students at the university. So overall, this whole thing is situated in the realm of computational photography. I think all of you probably have at least one computational photography device around. So I think the smartphone is really like the thing that made things really popular in this realm. But maybe to recap a bit on the basic idea behind all of that, what we want to do here is to have some modifications to our traditional imaging pipeline, so we are able to then acquire some richer acquisition of data of our scene, basically. And we can do a couple of modifications there. One example would be to add a light source, some structured light, for example, some pattern. We can also add something to the lens itself. For example, put some coded aperture at the aperture plane, or add some lens grid right before the sensor, which has been done for the light row or light field applications. We can also do some modifications to the sensor itself, just by activating different pixels, having pixel shift, have the whole sensor shifted around for super resolution applications and these kind of things, or stabilization. And in the end, we want to have some processing, which probably should be a bit more elaborate and complex than the traditional pipeline in a digital camera. And together with that, then to get our application-specific or non-specific data out of that, which is hopefully contains more of the original data present in the scene. With data, I mostly mean light in our case. So if we talk about the task of optical coding or programmable optics, we mostly are concerned with optics and algorithms, which together make up this computational pipeline. And here in this figure, we can see actually an object that's emitting some light waves. So here for this talk, we will also look at light as a wave more than a ray, which we're probably more used to in the daily life. And we add some coding in between our scene and our detector. Detector would be the sensor in our case. And this encoder part, which I usually refer to as the encoder, would be, in this case, some element which we can actually control with the device, like a monitor, and then impose some specific coding to our optical system. And afterwards, we have a decoder, which then, again, takes our encoded image and reconstructs some data out of that coding. And we can start this approach from different sides, but ideally you want to optimize both parts to make up for one optimized case. We have seen this major success of all the deep learning and machine learning in the past couple of years. And obviously, this is also something that can be applied here, especially for the decoding part. But we can also see later that these differentiable or auto-diff networks are really helpful in designing these kind of pipelines. So but why why this whole thing? And this is a really good question. So I hope I can give you some ideas why this can be really interesting, not only for the film and animation industry, but like the overall application of computational imaging devices. So overall, what we can achieve with this kind of setup, we can reduce complexity in terms of the optical complexity. So the glass, the optics construction that goes into a modern lens can be reduced by ideally maintaining a similar amount of quality. We can reduce the size potentially, by that also reduce material cost, because those devices that I'm going to talk about are pretty low cost actually. And by offloading some of the processing tasks to the optical part of your system, you can also potentially reduce energy in processing. And in the end, probably most important to us, it could also help to give us some more or new ways of artistically working with lenses by changing parts of the lens with the program, basically. So I already started with some motivation, some lengthy motivation. Actually, it's almost the whole of talk now, if you look at the time. But I'm also going to show you a bit more, which first of all will be one camera design, which has been built at the University of Tübingen, which is the wavefront coding camera, one that in a second. And I'm also presenting some experiments that have been conducted, some results, and give you a bit of an idea of where this could lead in the future. So wavefront coding. This is a term that actually has been coined by Dowski and Cathy some while back. It's in the 90s, I think, or 80s even. And they, what they were doing, or their goal was to actually extend the depth of field of a lens, or at the same time do some depth sensing, which means getting from your something like depth from defocus, kind of. So getting from your image blur amount the distance to your object or your pixel. And they did this by introducing some kind of mask or some optical element in the pathway of the light, which would change the phase of the incoming light. We can visualize this by looking at the point spread function, actually, which we can see on the right. So these small dots here on the left would be the image of an impulse response, or it would be the impulse response, the image of an impulse, which would be a point light source, basically just one point light source, which is at the focus plane. And yeah, this would be then the image formed on the sensor. Ideally, this would be just 1 pixel, or smaller than 1 pixel. We can see that for lower quality lenses, this looks differently, and especially if we change the distance of our light source, it would get defocused, and we get a PSF that looks like the one on the right. You can probably think of this more or less like a blur kernel of your image, and this is also how we can formulate then the image formulation, which I'm going to talk in a second. But again, back to the idea of the wavefront coding here, what we can do actually by placing these kind of weirdly shaped objects in our pathway, we can then achieve a point spread function that looks more or less the same over a large distance or a large range of distances. So the focus plane one on the left looks pretty much the same as the one on the right, which is taken at the same distance as the regular one on the top row. And by this, we can actually manage to control the blur in the image, and then to do some deconvolution afterwards to reconstruct the image. So as I said, convolution would be the really, really simplified way of describing this kind of image formation. So if we know the PSF, the point spread function, also referred to as the fingerprint of our optical system, then we can take our ideal image or our latent image, the one that we actually want to have, and convolve it with our PSF to then get the actual image that's forming on the sensor. And we can undo this operation by kind of deconvoluting our image. So taking a known PSF and trying to invert that. And then, do this. And we can already tell this inversion might not work perfectly. It's probably an ill-posed problem. And to get around this, it's really interesting or important of how you construct these PSFs or these functions to retain as much information as possible when you do the inversion. So for the coding itself, to make this thing programmable, we use this spatial light modulator, which can be thought of as basically a liquid crystal display. So we have this small item, which has, I think, full HD resolution here, a lot of liquid crystal displays, and those liquid crystals, they actually interact with the incoming light and have some phase shifting effect. In other words, or make it a bit more relatable, it's actually changing the refractive index of our pixel at this position. So for each of those positions in our spatial light modulator, we can change the refractive index to a certain amount, and by that change the pathway of the incoming light. One easy thing to do then would be, of course, we could do some focusing or replace basically a simple lens by our SLM, and then display something like this Fresnel lens pattern, and by that actually generate a pattern that looks a bit like this. So this would be the phase pattern that we can display then on our SLM, and by this focus the rays towards our sensor. And this actually works. I'm going to show a couple of examples later without changing or moving any of the optical elements. In fact, actually, even without having any glass object in the optical pathway. So in the lab, it looks a bit like this. So we would have a polarizer in the beginning, which is actually important because those liquid crystals, they only work on polarized light, unfortunately. And then we have here on the 2, which is actually the SLM. Here in this case, it's a reflective SLM. There are also other options where you can actually have a transmissive approach where the light goes through the element. Here it's reflecting back, and then we have our camera here. The reason why this is kind of a Taylor lens is actually that we kind of fake our SLM to be at the aperture plane. So we want to just reduce the amount of parallax between the two objects by having a long focal length here. This is just like a prototype thing, so I think that's probably obvious. But with this setup, we can do some interesting things. So I already mentioned the idea of the PSF to be something like the blur kernel, and by changing the shape of our PSF, we can change the shape of the bokeh of a lens, and we can actually do this by deciding for some shape and then optimizing for this shape using some traditional way of data fitting, kind of. So we have a lens model, like a simplified optical model for our SLM, for our face coding, and then we have some target image that we want to show at the sensor plane, and then we can optimize for a phase pattern that actually leads to this one. There might be multiple solutions, but we can get one, and by this one, we can then generate this kind of shapes. For example, even an animation of the PSF is possible since we have basically a display device that has a refresh rate of 60 Hertz. Come on. So next one would be just how this would look like with an image convolved with a spiral PSF. And here, as I promised, some result for focusing, actually. Oh, sorry. We missed it. So we focus from the back to the front just by changing the programming on the SLM. Another thing that can be done, which has been done actually by Chen, is using some, basically trying to get more wavelength or more color bands out of the captured images. And we can do this by exploiting the wavelength dependency of the PSF, which means that for different wavelengths, our SLM has a different refractive index, and we construct PSFs that are actually kind of sensitive to wavelength. For example, this ring PSF is pretty well suited for that because it also shows basically a fringing in all directions, which is what we kind of after that. And then, we can invert that or reconstruct from this, up to 6 bands. Actually, we extended that work even to up to 32 bands by using the neural network for the reconstruction afterwards. This can be really interesting for surveying or high-quality scans, for example, more than the regular photographer. But yeah. And as I said already, you can also do extended depth of field, which might not be the most important application. But in this context, it's really interesting that we can actually exploit a different scheme for the optimization here. Because what has been done here was to implement a fully differentiable optics model of the image formation process. And then we could, given some loss function or some criterion for our application, we can actually optimize both the reconstruction process as well as the pattern itself. And from that, we got out something that looks a bit like this. So similar to the one that I showed on the first slide, which is then a phase. This is basically a phase pattern for a chromatic extended depth of field. We here approximated the wavelength dependency of the SLM, but it doesn't really matter too much. And we get out from simulation, things like this. So for a pretty wide range of different distances, we get a reasonable sharp image out here. So the first column would be the ground truth, and next to it, the reconstruction. And this is the image that's formed on the sensor. So it's blurry, but the interesting thing is here that it's actually the same kind of blurriness over the whole range of distances, and it's also a kind of blurriness that's good to invert. So it's an optimized PSF that seems to be invertible, at least it is for this kind of decoder, which is in this case some kind of UNet. Not sure if you're familiar with that, but basically a convolutional neural network to do that. This is another example from a color image for a pretty extreme distance of just half a meter, and the focus distance has been something at 2.5 meters. So the way that has been here, this generated is just like a plane that's actually put in front of the virtual sensor, kind of. So, and for the future, maybe another or final application, where here the idea is, maybe we can get it, or we want to change the field of view after the fact. So just take one image of a scene and then get out multiple different field of views, which would more or less correspond to different focal length. And for this, we can also use SLMs, but we have a bit of a different optical setup here. So we would not have the SLM at the position of the aperture, but move it a bit and have an intermediate plane where we actually form an image. So we have a lens still in our setup. And we have this SLM then, which does some coding to the image by basically changing, or we can visualize this as a change of angle of our chief ray, which goes to the center of our pupil here. And by that, we can actually change the magnification, so to speak, or distort the image. In simulation, this looks pretty nice, actually. For example, here with the sine wave, we can actually distort the image quite heavily. In the real world, it's not that well, actually. You can see maybe on the right here, there's a bit of distortion going on, but it's really like a very local distortion. And this is just a constraint of the spatial light modulator that we have here. There has been some advances, but still it's limited. Like the overall power, the refractive power of this device is not comparable to a big piece of glass, at least not yet. So in summary, we saw this computational camera setup, which can do some things to our light waves in a way that we can control with something, it's just a regular GPU basically. And we can do this, we use this to control focus, to do some multispectral capturing. We can do end-to-end joint design for a specific purpose. We can have also seen for some other works which do this, that they offload basically the first perception layer of a classification network to the optics itself, and thereby also saving some energy for the computation afterwards, for the classification itself. And ideally, we can also distort our images. If we would use, for example, 2 spatial light modulators, we can even do this without an extra lens in the setup. So this would be it, basically. So the ideas in the future, hopefully, maybe make this work also for smaller devices outside of the lab, lift some of the limitations that we still have from the computation, from the SLM itself, and also use maybe this time multiplexed aspect, because the nice thing is, especially with these liquid crystal based designs, that we can actually have different tasks in one optical setup. We can even change that in a blink of a second, we can capture exposure series with different point spread functions, for example, to also then generate or decide afterwards which kind of bokeh you want to have, for example. We can also calibrate for other lenses and even simulate this kind of point spread function. As I said, this is like really a parameter that's specific to a certain lens, and one might also be able to really have some quite heavy distortions from old vintage lenses reconstructed by this kind of approach. And as I said, lastly, it would also be interesting to offload some tasks to the optical design. This points towards optical computer, which is really nice because we are having almost no energy and it's working at speed of light. So I run massively over time, but I think if there's still questions, let me know, and also feel free to get in touch with me. I'm always happy to share some thoughts on that.